Okay, let's get started. Do we have any question? If not, so last week we introduced Grover's algorithm. It's this algorithm that lets you use square root n queries or query guess to search mark item out of unmarked items. Okay. So this is a polynomial speed up over the classic algorithm where you want to search through n items. You need to use theta n query and time. And so this is an improvement, and we want to see whether this is optimal. And and indeed this week we are going to show that the Grover search algorithm is actually optimal. Okay? And so that means that that means that for any quantum algorithm that want to do this unstructured search problem, you actually need to use omega n query and time. And we're also actually going to give a query complexity lower bound, and that will also be a time complexity lower bound because we think each query need at least one step of time. Okay, so we are going to show that the Grover search algorithm is very nice. It's not only faster than classic algorithm, it's actually optimal over all quantum algorithms. Okay, and so I will say something a little confusing. Sometimes I say lower bound for Grover search, but really, I think an important thing to know here is that this is not a lower bound for just Grover search algorithm. Okay, so we're actually doing a lower bound for the search problem. Okay, so we are doing a lower bound for this problem where you are given your input this f of x, and they want to see whether f of x equal to O0 or there's some x. Such that f of x equal to 1. Okay. And so you can use any quantum algorithm on this search problem, but we are going to show that whatever algorithm you do, if you want to solve this problem with good probability, then you need omega square root number of queries. Okay. And so let's see the search problem once again. So it's a bit funny. It's a decision version of the search problem. So you want to do a decision. You want to decide some yes and no function based on your input small f. So you want to say whether small f of x equal to 0 for all x or small f of x equal to 1 for some x. Okay? So you can see this is obviously a yes or no. And so search problem was harder because search says if f of x equal to 0 for all x, you need to say it's O0, and if f of x equal to 1, you need to give out some x. You need to not only say it's no, and you also need to give the x such that f of x equal to 1. So so the Grover algorithm was able to find a mark item, but here we make this easier version, and we say this easier version of the problem is still very hard. So Grover's so the original search problem is even harder than this decision version, need omega square root number of queries. Okay, and so this is what we want to do. Okay, and so if that's correct, then let's start this query complexity lower bound. Okay, and so in general, it's very hard to bound the time complexity everything. So we go to this query complexity problem. You see now this problem is input is encoded in this weird oracle and f of x, and this gives us information theoretical way to say how many times the zero algorithm need to call this OF to actually learn enough about OF to do the decision. Okay. And so here is a schematic of a quantum algorithm. So quantum algorithm will be, so we think about quantum query algorithm and think about how many query you use. So you are going to place a whole bunch of OF inside your algorithm because you need to learn enough about f, this small f, to solve your decision problem here. Okay? And then in between those OF, we say we are just going to do whatever arbitrary unitary. But the important thing here is that all those UK doesn't call the oracle, so those are independent of your small f. So you can do arbitrary thing because we don't care about time complexity. Here we only care about query complexity, only care about how many OF you use. Okay, and yeah, so you have a whole bunch of things that are arbitrary as long as it doesn't depend on small f. And yeah, so it's between those OF, and you have the OF in between. And you ask how long does this sequence need to be for your algorithm to successfully solve the problem here. Okay, so you have this U, O, U, O, U, O, and U0, OF, U1, OF, etc. And let's say we use a big T query. Okay? That means that there are basically big T layers here. And then what we will do is so important thing here is we are going to track how the how the quantum algorithm change. Oh, it's sorry, it got clipped by the picture. Okay, so we have those psi t f here. Okay, so there should be f here. Sorry for the cropped picture. Okay, so those should be f here. Yeah, and so we are going to track and oh yeah, so we're going to track just the state before each OF. Okay, and we are going to track how those states depend on f. Okay, because this thing should so we think about changing our small f. So those u should be fixed, they depend on small f. And so we are going to track how the state of the quantum algorithm change depend on your small f. Okay. Okay, so we think about this. So we think about what happens if you change a different small f, and we kind of think about how the trajectory of the quantum algorithm. So maybe let's draw here. Okay, so we kind of think about how a quantum state grows. So your psi f and psi f prime. Okay, we kind of think about how the state of the quantum algorithm evolves throughout application of this case, and what's happened when what's how the distance between those states, the distance between different f and f prime, how this evolves throughout the algorithm. Okay. And so I draw this as I draw this schematic with the beginning together, because at the start of the algorithm, no matter what your f is, the quantum state should be the same. So because it's just all the starting state is O0, because the inputs are only in those OF, and so we just start our quantum algorithm with O0 input. Okay, and yeah, so for OF. The start, okay, so we actually think the start is here, because you start with O0 and you apply this U0, so we start with this psi F0, but the psi F0 should be the same for every F, because up until here, nothing about small f has happened. So you start with everything being the same, okay? And yeah, so and I want to track the distance between different psi f and psi f prime when your small t evolve, and so you know when small t equals 0, they are the same. And and at the end, then we think it's actually some of them should be very far away. Okay, and so which one of them should be far away? That's when you need to make a decision. So you want to make a decision at the end, so we didn't draw it here. Okay, by the end you want to do some measurement and make your 0-1 decision, right? At the end of the algorithm, you want to measure your state in some basis and make this yes or no decision. You want to decide your small f it give you is a yes instance or a no instance. Okay, and now I give a slightly confusing notation. Okay. And so the big F is for this search problem. So the big F is this problem where you want to decide. Big F is you want to decide whether small f has any mark item. Okay, so this thing is big F. Okay, So we have a little confusing, but we have a big F on small f. So small f is a function, but it's also the input to the bigger problem we want to solve. Okay, so and anyway, so if your input string, so your input string can be either give you a yes answer or a no answer. Okay, and if the answer is different, then the quantum algorithm at the end should give you different major outcome. Okay. And we are going to show more rigorously later. If you want to make a measurement to distinguish two states, then those two states must be pretty far away from each other. In some sense of far away, and we are going to show in this sense. Okay, means that the absolute distance of the two states need to be pretty far away. You want to make be able to make a distinction between whether big F of small f equal to 1 or big F of small f equal to 0. Okay, and because you need to make a decision at the end, so we know that the psi f big T and the psi f prime big T should be pretty far away and distinguishable. Okay, and once again, big F is the quadrant we want to solve, and in this example is this decision version of search. And then small f is actually an input string. We think about it as a big and big input string, where so it's a truth table of your small f from small f of 0 to small f n minus 1. Okay, and and once again, our example is big F is search. And our small f, if we want it to be, I guess, a yes input, then small f should be O0, and we want to be an O input, then our small f prime can be anything but O0, but we actually restrict to a special case such that it's easier. So we think about where it's just a one-mark item. So we are distinguishing, we will try to distinguish small f that's O0. So let's say our small f, there is only one yes instance, and it's the O0 string, 0, 0, 0, 0. And the f prime, there are many possible f prime that give you no answer. It's either 1, 0, 0, 0, 0, or 0, 1, 0, 0, 0, 0, or da da da. And 0, 0, 0, 0, 1. Okay, and so and so all those so this small f give you big F equal to yes, and this give you no. And we think about kind of we can have many pairing. Okay. So we can have this f pairing with this f prime, this f pairing with this prime, etc. Okay, and then they all need to satisfy the analysis we had before. Okay, so it's those two things. So for each pair, let's start with because everything starts with a same. So for each pair, the distance start with 0, and at the end, the distance need to be something big. And by big, we need, okay, so this is far away here. By big, we mean some constant. So maybe like 1/3 or something. So this is a constant. Okay, so you start with 0, and you end with a constant far away. Okay. And then how does this help us bound the query complexity is that then we think about how so back to this algorithm, and we think about how the state and the distance can change. Okay, and then you will see that the only thing in middle are those u and o, and the u actually does nothing because u doesn't depend on f. So if you apply u on this psi f t and psi f prime t, then it's a same unitary apply on two states, then it doesn't change the distance between those two states because unitary preserve distance. So the only thing that will change the distance between your psi f and psi f prime are those u and o f, because one of the lines get applied OF and one of the line is get applied OF prime. Okay, and yeah, and so as we say here, so UT doesn't change the distance, and so it must be those OF or OF prime that will separate your psi f and psi f prime. Okay, and we know that you start with the distance 0 and you end up with some distance constant. Then we think if each OF doesn't increase the distance too much, then we need a lot of OF to get the distance separated far enough. Okay, so that's the idea. But here is a big caveat. Okay, so we think okay, so what if we just trigger one pair of f and f prime? So maybe we want to see how many query do we need to separate this 00 input string and this 1000 input string. Okay. And how many query do we need to separate those two strings? So let's say we want to separate this string. Excuse me. Where am I? Okay. We want to separate this string and this string. How many query we need to use is actually one query. Okay. Because if you query at the first location, so if your input state is just 0, and you query the first location, you see that you can just distinguish this f and this f prime very nicely. Okay, yeah, and so for a specific pair of f and f prime, the distance of the state can actually change a lot because you can just query at a location where the f and the prime are different. Okay. And so you see that, okay, so one query is enough to distinguish them. Okay, and that don't give us a very good lower bound. Okay, and so the trick is that we think the trick is that we know our program, our algorithm need to separate this f from all possible f prime. Okay. And so not only do we need to distinguish this input from this input, we only need to distinguish this input from all those -1 different inputs. Okay, and so if you look at the first location, then you see those two are different. But if you look at first location, you don't see this f different from this f, this f prime or this f prime or this other f prime, where the first location is 0. Okay. And yeah, and yeah, so here is yeah, and so the thing we'll do is we are going to sum over all the different pairs of those f and f prime, such that the sum of distance doesn't change a lot by just on average, doesn't change a lot on average by just querying by each oracle code, which we'll see in more detail later. Okay, and yeah, so we'll actually summing over all those pairs. So we think about we have many pairs here, many pairs between f and f prime, and the sum of distance. And so each pair has those distance to track. And then we think about if we sum them all together, then each query don't change the sum too much by on average. Hey, and yeah, and in that case, then we can track that this sum of distance start with this sum of distance will start with 0 and end with number of pairs times some constant. And if it doesn't change too much each step, then we need to do many steps to get the end we want. Okay, I think it might be a little too abstract to understand, so maybe let's go to the actual technical proof. But anyway, anyone has a question so far? Not, then maybe let's go to the actual math. Will be a little more clear. Okay, so yeah, now we define, give a bit more notation for our f and f prime. Okay, and so f is the yes input, and as we say for search problem, only yes input is this audio string. Yeah, or zero input. Okay, so we say we call this f0 tilde is the f such that the f of x equal to 0 for for all x. Okay, and then we need to define other f. So we want this f prime such that it is a unique market item. Okay, and we give them some index. We index it by this x. Okay, so x from 0 to n minus 1. Okay. because we come from 0. Okay, so for x from 0 to n minus 1, we define this f sub x, and it's small f with a unique market item where the market item is at this x location. Okay, so f sub x equal to f sub x of x equal to 1, and if you have some y not equal to x, then it's 0. Okay, so maybe let's go back to our block. This is a box notation, then or it's all 0 and 1 somewhere, and 0 otherwhere. Okay, and this is x location, and this is f sub x. Okay, f sub x is a function where the xth item is marked. Okay, and yeah, and now we want to compare the pairs, the different n pairs, the different pairs of f tilde 0 and f sub x. Okay, and before we go to the distance, the sum of distance, we need to say a little more about our oracle. Okay, and so we assume our oracle is the face version of the oracle. Okay, so this OF of x equal to minus 1 to the f of xx. Okay, so this is a bit for simplicity because this is a bit weaker than this oracle is actually a bit weaker than the computational basis oracle because you don't have a control, but we'll just say the extension to control if it's not too hard. Okay, so we do this kind of easier version of the proof. Okay, so we assume our OF is this face version, so it acts on computational basis x, give you minus 1 to the f of xx. Okay, and then we can think about what's the OF for the small f we actually care about here. So OF 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 tilde of 0 is actually identity. Okay, and this makes things a lot easier because then we don't really need to write about any of this. Okay, and it's identity because f tilde sub 0 of x equal to 0 all the time. So x on x is just 1 every time here, and this is just identity matrix. And let me think about what's O f sub x y, and then you see you get a minus 1 if only if x equal to y, because you only have this one market item. And you can write this as identity minus 2 times projector of y, because if y equal to x, then you get a minus 2 here, and minus 2 on this 1, it becomes minus 1. And if y doesn't equal to x, then if y doesn't equal to x, then you don't have this thing, and it just back to its identity on y back to y. Okay, and yeah, and now we change our notation a little bit more because we find out that we don't need to write this or f tilde sub 0, and so we actually don't need to write this small f anymore, and we just call this O f sub x as OX. Okay, and yeah. So the oracle we have here are those OX related to this f sub x, and then OX we actually have a very close form because we see OX any state y equal to this I minus 2xxy, And since y is any computational basis state, then by linearity, y is any computational basis state, and the previous part doesn't depend on y anymore. So we can have OX just equal to I minus this 2xx. Okay. So yeah, OX, we see that OX equal to this OF sub x is just equal to this thing. Okay. Because this expression doesn't depend on y anymore. And yeah. And it works on every basis element y. Okay. Yeah, so that's our notation and more notation. So we make our psi ft psi ft notation more formal. We use t here, but we use t here, but now we use k. Okay, so it's just switching t to k. And so before we have this phi ft and sorry, psi ft, and psi ft is you start with 0 and you go through t layer of those u and o. Okay, so you start with 0, then apply u0, then uox, and u1 and ox, da da da, to sorry, of and uk. Okay. And yeah, and now we just change the notation a little bit. And so once again, we don't want to write this h small f, and so we just call this psi x and sub k. Okay. And so this is state for this is state for your input is f sub x. And I guess once again back to this. This is after k layers. Okay, so you have some k layer here. After the k layer t, then that will be your psi xk here. Okay, so you start with 0, apply u o, okay, with some o with 0 o equal to ox. Okay, and so this is when your oracle has mark item on x part. And if your oracle has no mark item, and here we just have no script, so we just call it psi k to have a simpler notation. And that's just once again is start with 0, and you have a u of. But as we say, when your f is just o0, then your of is just identity, and so we don't even need to write o here, so it's just 0 with a whole bunch of u, with k different u, and that's a state. After k times step, k layers, this is a quantum state of your algorithm after k layers with oracle being O0 string. Okay, and okay, so those two things, and finally we can define this progress function. Oh, sorry, I should have this bigger. Okay, and so this weird sum of distance we keep talking about. Now we have a very mathematical form here. Okay. So we want to have a distance between all pair of psi k and psi xk. Okay? So we have a distance between psi k and psi xk. So this is just everything. This is a vector. This is a vector because those k states are vectors. Okay? So vector minus vector is another vector. Then we just have the norm of this vector squared. Okay? So we have this distance, and as we say, we want to sum over all pairs, and so we sum over OK. Okay. So we sum over, not sum over k, we sum over ox. Okay. We sum over ox from 0 to m minus 1. So all possible location of the mark item. So psi x sub k minus psi k squared, and sum over all possible x. And this thing is a kind of a progress function we want to check. Okay. And we call this thing dk. Yeah, and later on we will even get even more sloppy about notation, so we don't even want to write this kit anymore, and so we just write psi k kit as psi k and psi xk kit as psi xk. Okay? So this is kind of pretty bad notation, but this is what we'll do. Yeah. So please remember that we are doing this, and actually sometimes we'll make the kit back. And yeah, So this is more notation. And anyway, so this progressive function has a property we want to say. And so it starts with being 0 because as we say, all those psi fk so the psi xk or psi k, they start with you see when k equals 0, they start with being u0 0. So u0 0 u0 0. So when k equals 0, they are just the same. Okay, and so k equal like I say, we can say d0 equal to 0, although it's yeah. So we know that it's d0 equals to 0, and we are going to show maybe next time d sub t equal to omega of n. Okay, so basically each one for every x, this is psi k, this psi x and psi when at the end of logarithm. So we think at the end of logarithm t, we have a big T queries. And as we said, at the end of logarithm, you want to make a measurement to distinguish whether it's a 0 or yes case, and that means that because you want to make this yes or no distinguishment, so at the end, every f and f prime need to be pretty far away, and that means that, every psi f and every psi f prime need to be pretty far away, and translate to notation here, that means, every psi x and every psi need to be pretty far away. Means there is some constant distance between this psi x t and psi t. And so we sum over n of length, so this thing should be omega of big N. Okay, so I start with 0 and the end with n, and then there's this technical part here. We should have time to show today is that actually the d of k doesn't grow too fast. So as the k increase, this actually only grows quadratically with k. So it's order k squared. Okay, and so we combine those two conditions. So you have something that only grows as k squared, and at the end you need and at the end when you use a big T step, this thing should grow to big N. Then you need your big T to be at least square root of big N. Okay, so this is a high level idea of the proof. So you think this progress measure cannot grow too fast with k, and but at the end you need to be pretty large. You need to grow into a pretty large number, which is big N, omega big N, and so you need to go through square root n steps. Okay, any question? If not, yeah, then let's go to see the most technical part of whether this thing only grows as k squared. Okay. And we shown by induction. Okay. So first part we show dk is actually less equal to a very precise number for k squared here, and by induction. So we have the start of induction. We see what if k equals 0, and as we say k equals 0, this is very easy. D0 will equal to 0 because everything starts at the same state. And 0 is less than 4 times 0 squared and equal to 0. And so, yeah, at k equals 0, the induction step is satisfied. Okay, the starting condition is satisfied. And then by induction, so now we assume dk less than 4k squared, and we want to show this thing holds true for k equal to k plus 1. Change k to k plus 1. So we think about what is dk plus 1. Okay. And dk plus 1 is, well, psi k plus 1 x minus psi k plus 1. Okay? And psi k plus 1, we think about how psi xk change to psi k plus 1 is you will get the extra ox and the extra layer of ox and uk plus 1. Okay? And for psi k, because the oracle is just identity, you only get the extra uk plus 1. Okay? And so dk plus 1 equal to the sum x UK plus 1 OX psi x minus UK plus 1 psi k. And then as we said before, because you have UK plus 1 on both of them, but the UK plus 1 actually doesn't change the distance between two quantum states. But this is a quantum state and this is a quantum state. And then we want to see the distance. And UK plus 1 doesn't change the distance no matter what the UK plus 1 is. And so we can just get rid of it. And so this is summation x or x psi k, psi xk minus psi k squared. Okay. And then now we do kind of funny thing. We break the difference between those things into the difference between two different terms that are easier to measure. So we're actually subtracting and adding and subtracting one term here. So adding and subtracting this weird OX psi k term. Okay. Okay. So this is a clever step because we know this makes things easier. So you see we have OX psi k, extra OX psi k term on here, and so we are subtracting OX psi k. Let's see, it should be OX psi k. We are subtracting OX psi k here, and okay, so I believe this should be a plus sign here. Sorry. Okay, so that's why it's a little weird. Okay. Okay, so we have we are subtracting OX psi k here and adding OX psi k here, so they cancel out. And so now with one difference, we're breaking into two differences that are easier to measure. So we have OX of OX psi xk minus psi k plus OX OX minus identity on psi k. Okay, and yeah, everything checks out. And then we have this square, non-square of this thing. And what we are going to do is we are just going to use here we are, sorry, we're missing a square. Okay, so we are just going to use some b plus c squared is less than b squared plus 2 non bc plus non c squared. And here b and c are both vectors, but these inequalities are true for vectors. Okay. And yeah, it's pretty easy to show by some Cauchy shots. And so we are going to break into those terms, and now we think about what are non-square of those b term and the c term here. So this first part will be b, this part will be c. And we actually deal with C first. Okay, so what's this C term? And so remember, OX was the identity minus 2XX. And so if you subtract out the identity part, then you see that this OX minus I is very easy. It's just minus 2 times XX. Okay. So yeah, it's minus 2 and then xx on psi k. Then now we remember psi k is actually a ket vector. So we have this x on ket vector, it becomes a number, and you left with this x ket. Okay, and yeah, and so we subtract those things back, and we see that dk plus 1 is okay, and so this should be plus again. Okay. So dk plus 1 is this thing, and you use this inequality, so it's less equal to okay, so we have some x on outside and breaking this b plus c square thing, and so we have b square, and so b square once again this you have ox outside, you have ox on everything, and ox although ox depend on your f. But here we just have a fixed OX here, and OX is a unitary, so once again a unitary doesn't change your non-square. Okay, so you can get rid of OX here. Okay, so this is just psi xk minus psi k squared, and then you have this 2bc squared, 2bc term, and so you have 2, and then b non, as we know it was this psi xk psi k non. And C non is this non minus 2 and minus 2 and x inner product with psi x, and then you have non on x, but the x is just a computational basis state, and so norm on x is just 1. Okay, so here we should have right, this is 1. Okay, and so norm of this thing is just 2 times the norm on this number x and x in that part with psi k. Okay, and yeah, so you have 2 here and 2 here, and so you get plus 4 here. And at the end, then you have norm c squared. Then norm c we just say is 2 and 2 and norm on x I x. Okay, and yeah, and the square, so it's 4 on norm x I k. Oh, so yeah, sorry, there's a typo here, so it should be not psi x, it should be psi k here. X psi k. Sorry, a little typo. Yeah, and yeah, so that's breaking these things with simplification we can make. So basically, we see that OX makes the identity has a very simple form, makes the latest term a lot simpler. Okay, so made the norm of the latest term. So basically, we have that this norm C equal to just 2 and norm x psi k. Okay, and yeah, so then norm c squared is 4 norm x psi k squared, and 2 norm c is 4 and this norm x psi k. Okay, and then we can actually simplify this norm c a little more. So norm c squared is this norm c sorry, wrong direction. Okay, and now we do the sum x, then we see that the sum x norm c squared has some nice form. Okay, so sum x of the norm x psi k squared is so this norm square is this thing times its complex conjugate, which is just psi k x. Okay, and then we can pull the summation of x inside, then the sum psi k and the sum x xx and psi k, but the x are just every computational basis state. So if sum x here, this is identity, so this is just inner product between psi k and psi k, and psi k is also a normalized vector, so this thing is just 1. Okay, and so we know the latest term, this sum to 1, and also we are going to break the middle term with this Cauchy-Schwarz identity, Cauchy-Schwarz inequality, which is sum x ax bx is less equal to square root of sum x ax squared non squared square root sum x bx squared. Okay. And so we do this term one by one. So dk plus 1, we know it was this thing. Okay, and so we look at terms one by one. So we see that the first term is actually just dk, because dk is just sum x and psi x k minus psi k squared. Okay, so first term is just dk. That's very nice. So you can know the difference between dk and dk plus 1. And the other two terms are what's the difference between dk and dk plus 1. And as we say, the middle term we are going to use the Cauchy-Schwarz inequality, and so this part will be a, and this part will be ax, and this part will be bx, and so we have a square root summation x and ax squared, and square root summation x bx squared. And the last term we just say if you sum over all x, this thing is 1. Okay. So this thing is 1 times 4 is 4. Okay? And in the middle part, those two things, we see that they are actually familiar things. These are, once again, this is the dk, and this is the summation x xi squared we just said. Okay. Excuse me. And yeah. So this term is 4 actually square root dk times square root 1, which is equal to 1. Okay. So the whole thing together is dk plus 4 square root dk plus 4. Okay, and then now we can back to use our induction assumption. So we say dk is less equal to 4k squared, so less equal to 4k squared, and is less equal to 4, and the square root 4k squared equal to 2k, so this is 8k, and plus 4. Okay, and so everything together, this is equal to 4k plus 1 squared. So we see that if we have this induction assumption, dk less equal to 4k squared, then dk plus 1 is also less equal to 4k plus 1 squared. And yeah, and so the induction together will give us that dk is always less than 4k squared, and this is for all integer k that's greater or equal to 0. Okay, and so that completes the first part of our lower bound. And the next part we want to show is that yeah, and we have 5 minutes, so I guess we are not going to go through every of the next part. But basically, the next part we want to show that at the end we have the d of t, big T is omega big N. And as I said, the idea is, I think it's pretty simple. The idea is that at the end there should be a projector that distinguishes your if there should be a projector P distinguishes your big F of F equals 0 or big F of F equal to 1. And with some constant probability, you want some pretty good probability of success. Okay, and say your probability of success is A over 9. This was a bit closer to 1 to make the theorem a bit easier. Usually we would do 2/3, but here we say A over 9. It can be easily done by some amplification, just majority voting. And anyway, so if we have this thing, then we will want that the projector on the 0 input is pretty small. Okay, and yeah, so projector on 0 input we want to be less than 1 over 9, and so it means the accept probability is pretty small, less than 1 over 9. And the projector on the I guess we are no input, so when there is a mark item, we want to be pretty high. Okay, yeah, so the projector so when there is a mark item, we want the projector to say yes, pretty high probability. So so we want to say greater or equal to A over 9. Okay, and then there's a theorem we are going to show next time, saying that if those two states, if your psi t and psi xt satisfy the property that there is a projector distinction in this way, then those two vectors themselves must be pretty far away. And here we make a pretty abstract way. Abstract way to say this, we say if there is a projector such that projector on first vector A, where A is just this psi t, is less than its non-square is less than 1 over 9, and the projector on second vector B is greater than A over 9, then A and B must be pretty far away. So A minus B squared must be greater or equal to 2 over 3. Okay, and yeah. And this is actually an easy version of the proof, but I think we are a little short on time. So let's save the proof for next time, and just say you have this thing, and we put it on every psi t and psi xt pair. Then we see that for all x, the psi t minus psi xt minus psi t squared is greater or equal to 2/3, and so d big T must be greater or equal to n times this 2/3, and so d big T must be omega n and omega big N, and so combined with those two claims, combined with our 4k squared claim and this 2/3 big N claim, we have that we need big T at least omega square root n to solve our search problem. Okay. And yeah, so I think that will be today. So if there's no question, we can stop about 2 minutes earlier today. Okay, and yeah, see you next time. Next time we will finish the lower bound here. And talk actually a little bit about information theory. We will talk about different ways to do this lower bound, and yeah. This will go to you a little bit about information theory, about the relationship between distinguishing quantum state and the distance measures between quantum states. Okay, yeah, so see you next time on Thursday. And I guess I can also say, and since the semester are ending, remember the final will be in about 2 weeks. So we're already on 14th week. So next week Thursday will be our final. Okay, yeah. So see you.